Hello and welcome to our video lecture on set operations and compound inequalities. Before we can understand set operations and compound inequalities, we need to understand the difference between the words and or in mathematics. And the difference is quite significant from the standpoint of both logic and its closest relative, mathematics. When you say I'm either going to the movies or to a live show tonight, it's usually clear from context that you do not mean you're going to do one or the other or both. This kind of or, which usually indicates that you're going to do this or that, but not both, is called an exclusive or, which is the kind of or we usually use in a regular conversational English. In logic and mathematics, however, when we say this or that, we always mean this or that or both, unless specifically indicated otherwise. This kind of or is called an inclusive or. The way and, however, is used in plain English and in logic and mathematics is very similar and consistent. In both cases, this and that indicates both. Let's go ahead and try to visualize some of these concepts. One of the tools we use to understand the difference between and or is a logical truth table. So here we have two statements, P and Q, and we want to know, depending on the truth or false state of each of these statements, what kind of a state will P and Q have. Notice that if the statement P and Q are both true, then P and Q will also be true. But if either one of those is false, or if both are false, then the statement P and Q will be false. So in order for an AND statement to be true, both the statements in it have to be true. OR behaves very differently. An OR statement is true if either of the two statements is true. So, of course, if they're both true, it'll be true. As long as one of them is true, the OR statement is going to be true. The only time an OR statement is false is when both statements are false. So you see they behave quite differently, and it's this difference between and or that must be mastered if anything that we do in mathematics is going to make sense. After the mathematician George Cantor came up with the concept of sets and defined them, pretty much all branches of mathematics started to become defined using the concept of sets. So it's a very important concept. And a set is basically any unordered, well-defined collection of objects. The key concept here is well-defined. In other words, you cannot just pick any collection of objects and call it a set. At least not a mathematical set. Also notice that sets do not have to be ordered. Here are some examples of well-defined collections of objects which will be considered sets. The set of natural numbers less than 7. That's a perfectly well-defined set. We know exactly what is meant by the elements that should belong in that set. So that's what we mean by being well-defined, because that means we can clearly distinguish what's in the set from what is not in the set. Here's another one, the set of movies. By the way, for the first one, notice that's a very, very much a finite set because it has a finite number of elements, because the numbers are just 1, 2, 3, 4, 5, or 6, right? So in other words, we could actually write this set as the set containing 1, 2, 3, 4, 5, and 6. So this first set can also be described in that way. All right, and we call it finite because obviously it has a finite number of elements. Notice that each of these items within the set is called an element of the set, or we can also call it a member of the set. For the second example, we have the set of movies made in 2020. Notice that that will be a much larger set, but nevertheless it is still a finite set, because after all there were a finite number of movies that were made in 2020, and it will be a much larger set because many movies are made within a year on this planet, but nevertheless a finite set and well defined. We know exactly what we are dealing with. Here's another one, the set of planets in the solar system. This one may be slightly debatable because remember, poor Pluto keeps getting counted as a planet and then not, etc. But we all have a pretty good idea of what's in this particular set. The set of quadrupeds indigenous to Maui. Okay, so basically all the four-legged animals that are indigenous to Maui. So we know, again, much more difficult to come up with the actual members. You have to do a lot of research, but it is doable. All right, the set of all football stadiums, again, a much larger set, however, still manageable and can be done. You can come up with the elements, you know exactly what is being dealt with. All right, the set of all integers greater than 0. Notice that all of these other sets are finite. Here, for the first time, we're looking at a set that is actually infinite or infinite, because it contains infinitely many elements in it. You cannot count the number of elements. In fact, the set of all integers greater than 0 should be familiar to you because it has another name too. Let me actually write it out. Notice that it would be the set containing 1, 2, 3, 4, etc. The ellipsis here indicating that this set goes on and on, right? Notice that this set has infinitely many items in it, so we call it an infinite set. All right. Now let's look at some collection of objects that are not well defined and therefore would not be considered mathematical sets, right? So what about the collection of all cool people? Yeah, I mean, you may have an idea of what kind of a person is cool, but that may be very different from what somebody else considers a person who is cool to be. So coolness is not a well-defined quality, so that would not qualify as a well-defined mathematical collection, therefore not a set. The collection of all large numbers. Again, this is, you may go, hey, this is a math class. These are numbers. What's wrong with that? Well, what's wrong with that is that largeness is not really a well-defined quality, because what if I say to you, you say to me, okay, numbers greater than 1,000. Yeah, but that's your definition of what's large. Somebody else may have a different definition. There's no universal agreement on what's a large number, right? So we can't go by that. Now, if we one day as a planet decide, okay, we're going to call every number that's larger than so and so, we pick a number and say we're going to call that large, then from that point forward, this could be a well-defined collection of objects and it could be a set, but not at this time. The collection of all smart people. Here we go again. We have the same problem. You may have a good idea of what's a smart person, but it's not really a well-defined quality. So this would not be considered a mathematical set. Another way that we can appreciate the difference between and or is by looking at their set theoretic operations that utilize the concept of and or. The first one we'll look at is what we mean by the intersection of sets. That's an operation we can perform on two sets, and when we find the intersection of two sets like A and B depicted here as these two disks, actually, because it's not just the circle but the content within as well. So basically that's all the elements within this larger universal set U, which contains both A and B, such that X belongs to A. This little funny looking E here is actually not E, and it looks kind of like a C or a E, right? It's neither, it's epsilon. And what it stands for is in this context it means belonging to. So all X belonging to A and X belonging to B. In other words, to be in the intersection, you have to be in both sets. That's why this region right here is the only region that qualifies for an element which is in the intersection of the sets A and B. So this shaded region is the intersection of the two sets A and B. The union of the sets utilizes the concept of OR. So in other words, the union of A and B, A union B, is the set of all elements in the universal set which belong to A or belong to B. And remember, this is a mathematical OR. That means they can be in A, or they can be in B, or they can be in both. So that's why this part is included in the union as well. The only thing is, you don't want to count that part twice. Notice that the shaded region is showing darkness just because of the overlap of the two colors. Otherwise, what you want to do is, when you want to find a union of two sets, you want to merge them, but you don't want to double count, right? So don't repeat. In other words, you'll count the intersection only once when you want to look at the union. And then you can see the shaded region as the union of the sets A and B. So when you see intersection, think and. When you see union, think or. For our first example, we're going to look at these three sets. Set A is just a finite set containing 1, 2, 3, 4, and 5. Set B is the finite set containing 2, 3, 5, 7, and 11. They may appear familiar to you. They are indeed the first 5 prime numbers. Set C is the set of, notice that C is not given in the same format as these two. Here you're just seeing the list of all the elements that are in A and in B, right? We call this the roster method because every element is just listed, right? This here, this format for explaining a set is not the roster method because it's not telling you exactly what elements are in it, but it's giving you instructions for how to find those elements. So we call this set builder notation because it's giving you instructions on how to build the set. So here we have all X such that X is an integer between 5 and 10. So basically, notice I can easily construct that set because I know what is in it. So I can also write C in this format. I can say C. Okay, first of all, be aware of the fact that when we say between 5 and 10, that does not include 5 and 10. So be very careful with that. If we wanted to include those, we would say between 5 and 10, then we would put a comma and say inclusive, all right? And that would include a 5 and 10. But if we don't say that, that means it's not, they're not included. So basically, the only numbers in this set are 6, 7, 8, 9, and that's it. Those are the integers between 5 and 10. All right. Now we want to go ahead and perform some operations. We'll start with A intersect B, okay? So that means we're going to look at sets A and B, and we're going to determine what they have in common. Remember, we want all the elements that are in A and in B, right? Remember, and is the one that's difficult to please because it has to be in both, right? So what elements do you see that are in both sets? Pause the video, see if you can write it down, then come back. And do that with everything we do. Every problem that we do, you want to be ahead of the curve, right? You want to try everything on your own first before you continue. That's how you're going to awaken the logical part of your mind. That's how you're going to make leaps and bounds in progress in mathematics and all kinds of logical disciplines, okay? When you activate the mind itself and start to do things on your own, okay? If you just watch as if you're watching a movie, that's not going to get you far. Mathematics is not a spectator sport, right? It's a completely participatory sport. All right. So for A intersect B, we're going to get the set. We notice 2 is in both A and B, right? 3 is in both, and 5 is in both, and that's it. So the set containing 2, 3, and 5. That's the intersection of A and B. For the union of A and B, remember, we're going to merge the members of A and B. We're going to unite them, but we're not going to repeat, okay? So we get the set. Of course, since here we have all the numbers from 1 through 5, so we'll go ahead and start with that. So we want 1, 2, 3, 4, 5. And notice that we are also going to want 7 and 11, right? So we're going to bring those in from B, and we're not going to repeat any of the ones that we already got from A, right? And that's it. There's the set A union B. So merge, but don't repeat. By the way, you notice we're writing these in order. That's completely optional. It's kind of nice to do it. For example, if we all agree to do it, then all our answers are going to look the same. It'll be easy to verify, right, that we got it right. But this one, if you had written this instead, no one could find fault with that. Kind of imagine it like this. Imagine a set as a bag of groceries that you throw different items in it, right? When you go put different items in a grocery bag, is there any kind of an order to it? There isn't, right? But you know exactly what's in there, right? What's inside the bag, and that's the only thing that matters, right? It's exactly the same thing with sets. The order does not matter. So even though you will see me from time to time, or most of the time, kind of write things in order, that's just because it looks nicer and it's easier for all of us to verify that we have the same answer. Otherwise, remember, it's purely optional. I mean, order is not mandatory when it comes to sets. In fact, it doesn't even exist. It's not there. All right, now we're going to find the intersection of B and C. So here is B. Now I could look at this version of C, but it's much easier if I look at this version, right? So here is B, here is C. What do they have in common? Think about it and write it down and then come back. So I think you realize that the only item these two have in common is 7, right? So the intersection of B and C is just going to be the number 7. So this is a set containing just one element. All right. All right, how about B union C? So now we're going to merge B and C, okay? So what do we get when we merge these two sets without repeating, right? So basically, I mean, we get 2, 3, 5, 7. We are going to want to bring in, actually we are going to want to bring in 6. Now I know I'm kind of obsessing with order here, but that's just to make it look nicer. So we want 6, 7, 8, 9, and we also want that 11, right? Now verify that what we have just done is unite these two sets, B and C, without counting anything twice. So notice 2, 3, 5, 6, 7, 8, 9, and then 11, okay? All right, how about A union C? So now we're going to, yeah, so be careful. Sometimes they throw the orders off. These were, it was all intersections, then unions, intersection, then union. So sometimes in math books they do this to make sure you're awake, right? So A union C. So we're going to find the union of A and C first, right? So notice that we notice that we get 1, 2, 3, 4, 5, and then 6, 7, 8, 9. We just united and merged those two sets, but we did not repeat anything. Well, there was really nothing to repeat, right? Because they had nothing in common. That brings us to the intersection, right? Which is an interesting question. What do the sets A and C, right? What do these two sets have in common? And I think if you think about it a little bit, you will realize that set A and set C have no elements in common, right? So there are two ways we can show that. We can say, we can just put braces like that and not put anything in the middle. That means it's the intersection is empty. But more commonly, we write this symbol, which is, we call that the null set or the empty set. Same thing. Okay, and that's that. So yes, when two sets like A and C are lacking any elements in common, we call them disjoint. So we say A and C are disjoint sets. So because their intersection is empty, we can say therefore A and C are disjoint sets. All right, perfect. And that's how you handle a simple situation like that one. Very simple, very important. Make sure you completely get it and it makes total sense to you before we proceed. All right, when you go into your statistics class, if you ever end up taking such a class, then you're going to be encountering two types of what's called data, right? We call some discrete and the others continuous, right? It's kind of a short coming of many algebra classes where we don't kind of get into this concept more with you and get you more better prepared for, I mean, not more better, but better prepared for statistics. So I've decided to take care of that this time and do so for you. So basically, when we say a discrete data set, you have to be careful not just to call it a discrete set, because if you just call it a discrete set, then it goes into some more advanced mathematical topics. If you do a search on Google, it might confuse you. So, but if you put discrete data subsets, then you won't get confused like that, because the search results will be consistent as well. All right, so discrete data subsets are the kind of subsets of the set of real numbers where there are gaps between their elements. For example, the set of natural numbers, containing 1, 2, 3, 4. Set of whole numbers that just contains 0, 1, 2, 3, 4. And the set of integers, which contains all the whole numbers and their opposites, right? Now, there are gaps between 1 and 2, for example, right? There are gaps between 14 and 15. There are many, many numbers between 14 and 15. So therefore, we say there are gaps, right? Now, if, however, I look at a set like this, which says all x such that x is between 0 and 1, right? Now I'm talking about not a discrete set, but I'm talking about a discrete continuous data subset of the set of real numbers, because there are no gaps between the elements of this set, okay? In other words, what we mean, it's a subtle concept when you say there are no gaps, right? What we mean is that if you pick any two elements of this set, right, then you can find other elements of this set between those 2 points. Therefore, no gaps, right? Now, when it comes to the set of real numbers, which itself is a set which, has no gaps between the members of its set, you'll find that if you pick any two numbers, any two distinct real numbers, not only can you find one number between them, you can actually fit infinitely many numbers between any two real numbers, no matter how close those two numbers may happen to be. Take the number 0 and take the number 0.1. Now, those are pretty close, right? If you look at a graph. But guess what? You can fit infinitely many real numbers within that gap. The set of real numbers in that sense is referred to as the real continuum sometimes, okay? Because of that notion of continuity of numbers. It's truly a magical wonderland, and we'll delve into it a little bit here. So here is a real simple proof of why there are infinitely many numbers, for example, between 0 and 1. Remember, we can do this for any two numbers, right? But we're just picking 0 and 1 for simplicity. Note that if you take, for example, 1/2 and then 2/3 and then 3/4, notice what I'm doing. From each step to the next, I'm just adding 1 to both the numerator and the denominator, right? So then 4/5, then 5/6. Notice this process, you can define it and it can go on forever, right? There's no reason for this process to end. And all of them will be proper fractions with the numerator less than the denominator. Therefore, all of them will be numbers between 0 and 1. So here is a very simple and cute proof of the fact that there are infinitely many numbers between, for example, 0 and 1. Now, you want to get a more interesting proof, you can always set up this kind of a scenario, right? So here's another proof that there are infinitely many numbers between 0 and 1. This time, I'm going to get you infinitely many numbers between 0 and 1, and I'm not even going to go from any further than 0.12, for example, all right? So notice that I can start with the number 0.1, then I can pick the number 0.11, then I can pick this number. Again, this process can go on forever. And look at that, I haven't even made it to 0.2, and I already have what? And I already have infinitely many numbers that can fit between 0 and 1. So this is the case for any two distinct real numbers. You pick any two distinct real numbers, no matter how close to each other they may be, you can still fit infinitely many more real numbers between those two real numbers. This is what we mean by the real continuum. Now, of course, there are sub-continuums of real numbers as well, right? So connected continuums of real numbers, like the set of all numbers between 0 and 1, are encountered very often in mathematics. So it would be nice to have an efficient way of representing them. The notation that we use to do so is called interval notation. And that's exactly what comes in as an elegant and efficient way of representing continuous subsets of R. The set, which can be written using set builder notation like this, all real numbers x such that x is between 0 and 1, in interval notation just becomes a simple parentheses 0, 1 parentheses. This should not be confused with the ordered pair with an identical physical presentation, right? And whether we're talking about the ordered pair 0, 1 and or interval 0, 1 will always be clear from the context under discussion. So the notation all x such that x is between 0 and 1 has a name as well, as I mentioned already. It's called set builder notation, because you do not list the actual elements in the set when you utilize it. You only give instructions for building the set. We will now present some continuous subsets of R in both, in other words, some intervals in both set builder as well as interval notations. The set builder notation is not to be dismissed, however, because it's very descriptive. It has a lot of information that it reveals to us. So we're not going to be bringing in the set interval notation at the cost of set builder notation. We're just adding it to our repertoire of ways of presenting continuous subsets of the set of real numbers. Notice that when you're viewing the interval 0, 1, 0 and 1 are called the endpoints of the interval. With an interval, you always have a starting point and then an ending point, right? And of course, the interval will contain everything in between that starting point and that ending point. If you don't want to include a given endpoint in a set represented by an interval, you use a parenthesis next to it. So notice, since both 0 and 1 here have parentheses next to them, that means neither 0 nor 1 is part of this set. So this is strictly the set of the numbers that are between 0 and 1, but not including 0 or 1. When we do want to include an endpoint, we, instead of using a parenthesis, we'll use the bracket notation next to that endpoint. So any endpoint that has a bracket next to it will be included in the set represented by the interval. All right, so here what we have is some examples of what we call finite intervals. And remember, when we talk about continuous subsets of the set of real numbers, these sub-continuums, right, they're always going to have infinitely many elements in them, right? So this set between 2 and 5, the numbers between 2 and 5, is going to have infinitely many elements in it. So when we say finite, we're just talking about the length. Notice the length is final because it's just 5 minus 2, which is 3. The length is finite, but the number of elements in it is always infinite. So this is all, you can also get a little bit philosophical about this. So this is a beautiful example of infinity contained within finiteness, right? So here we're going to describe these subsets of the set of real number, these continuous subsets or continuums, right? Using words and then set builder notation and then interval notation. Notice that if we want to represent all real numbers between 2 and 5, now this is, I just picked 2 and 5 for simplicity. You could have said A and B, right? So this could be a very, very general discussion. If you want to get really general, just replace 2 and 5 with A and B. So notice that you want all real numbers between 2 and 5, and that would exclude 2 and 5. So it would look like this in set builder notation, all x belonging to the set of real numbers, or you can just say all real numbers such that they are between 2 and 5. So in interval notation, it will look like that. We just have starting point 2, ending point 5, and parentheses on both ends because we do not want to include them. When we graph that, we are going to want to have open circles at the 2 endpoints and then connect the 2 points. Notice that this set is actually on the number line. We just draw it a little bit elevated to make it easier to see. Otherwise, this set of numbers lives on the number line, okay? So for the next one, we have all real numbers between 2 and 5 left inclusive. That means include the 2, but not the 5. All right? So includes 2, excludes 5. So we write it like this using set builder notation, all x that is greater than or equal to 2, but less than 5, right? So basically in interval notation, it's going to look like this. Notice that if both end points are excluded, that becomes an open interval. It has to do with the fact that when you represent it graphically, we use those open circles, right? So this one, notice when one endpoint is included, the other is not, we call this a half open interval. Of course, on the end which the endpoint is included, we use a bracket. On the end where the endpoint is not included, we use a parentheses. Here, for the next one, we want all real numbers between 2 and 5 right inclusive. That means include the 5, the right endpoint, but not the left endpoint. So when you say right inclusive, you don't need to say left exclusive. It automatically means that, right? So in interval notation, it'll look like this. Parentheses 2 comma 5 bracket, because this time we want to include the 5 but not the 2. Remember, when you include it, use a bracket next to it. And of course, open circle at 2 because it's not included, closed circle at 5 because it is included. All real numbers between 2 and 5 inclusive. By the way, notice that the last one was also half open. But here we want the real numbers between 2 and 5 inclusive. When it says inclusive, that means include both 2 and 5, right? So here we're going to use brackets because they're both included, and we'll have closed circles at both endpoints. Remember, 2 and 5 are called the endpoints. Because both ends are closed, we call this a closed interval. So here we're going to look at some infinite intervals. Again, has nothing to do with the number of elements. They all have infinitely many points in them, right? Even the finite intervals we saw on the last page. So when we say infinite, we're talking about the length of the interval. Because it starts here, for example, and doesn't end, it doesn't have finite length. So here we're looking at all real numbers greater than 2. So in set builder notation, that'll be all x belonging to R such that x is greater than 2. In interval notation, we're going to have starting point 2, no ending point. So how do we indicate endlessness? Using infinity. So we say 2 comma infinity and we put parentheses. Okay, you never put a bracket next to an infinity or a negative infinity because neither is an actual number that you can include. Both of them are numerical concepts but not numbers. So do not ever use a bracket next to the right of infinity or to the left of negative infinity. Always parentheses. So again, this would be considered an open interval because we have parentheses on both sides. All real numbers greater than or equal to 2. Of course, in set builder notation, it'll be all x belonging to R such that x is greater than or equal to 2. So here, the beginning point is 2, so and it's included. So bracket 2, comma, there is no end, so comma infinity, and of course parentheses. This would be a half open interval. All real numbers less than 2, so all x belonging to R such that x is less than 2. And notice that here there is no beginning to this set. So we graph it like this. We start at 2 with an open circle and then arrow to the left, right? So in this case, we say that this is, to indicate beginninglessness, we use negative infinity. And so where is the beginning of this point interval? Well, negative infinity. Where does it end? It does end at 2, but it's not included, so we use parentheses. All real numbers less than or equal to 2. In set builder, it'll be all x belonging to R such that x is less than or equal to 2. That's a half open interval. So from negative infinity to 2, because 2 is included, we use bracket. That's what makes it half open. So again, we put a closed circle at 2 and draw an arrow to the left. All right, so make sure you absorb these completely before we proceed. In this problem, we're going to find the unions or intersections of some intervals. And if you recall, intervals are, after all, sets of real numbers. So set operations can be performed on them. Before we handle any of these, what we will do is we'll go ahead and take all the endpoints and we will plot them on the same number line, making sure that we respect their relative positions. So -5 being the smallest number is the first one on the left, then comes 5, and then 7, and then 10. It may not be drawn completely to scale, but notice everything is in a relatively correct position, so we can still get a pretty accurate graph. All right, so once we have the points plotted, then we'll go ahead and graph the intervals. Notice that the first interval named A, it has no beginning, but it does end at 10. So this arrow here pointing toward negative infinity, and then here we have a 10, but notice there's an open circle because of the parentheses. That means 10 is not included in that set. The next one is the interval from 7 to infinity, and that's left inclusive. That means it does include the 7 as an endpoint. So that's why we have a closed circle and then an arrow to the right. And the last one is the interval, the closed interval from -5 to 5 inclusive. That means including both endpoints. Now, and then we just have to connect them. Notice that all three of those intervals are actually on the number line, right? It's just we draw them a little bit raised so that it becomes easier to see them. So notice we've put a label of A on the green graph, which is the interval from -infinity to 10. We've labeled B, the second interval, and C for the third interval. So now we want to see what is the union of A and B. So we're going to take the set A, the green team, and we're going to merge it with the aqua team A and B, but without repeating. So what happens? Think about it for a minute. If you need to pause the video to think about it, do so. See what happens when you merge the green team and the blue team without repeating. What set of numbers would you end up with? All right, if you said the entire set of real numbers, you would be absolutely correct, because notice when you take the green team and the blue team and put them together, what real number is left out? None. Everything is included. In fact, these numbers here are included twice, right? The ones from here to here, except this one is not, right? But all the rest of them are counted twice, but we don't, of course, bring them in twice. We only need to list them once. All right, so this one is going to give us all real numbers. Notice we can write that as an interval, or we can just say R. We use this script notation to indicate that it's the set of real numbers. For the intersection of A and B, we're going to see what the green team and the blue team have in common. Notice this is the region that they have in common right there, from here to here, right? So notice that the blue point, the 7, is a member of the blue team as well as the green team, right? So therefore it's a member of both, right? So it is in the intersection. The 10, however, is a member of the, well, I should say aqua, really, aqua team, but not of the green team, right? So it's not in the intersection, so you have to be very careful with that. All right, so this intersection is going to be all the points from 7 to 10. Notice bracket at 7, parentheses at 10, because 10 is not included. All right, so next we're going to look at the union of B, which is the aqua team, and C, which is the red team. What do we get when we put those together? Well, they don't really have anything in common, so when you put them together, you're just going to get this set and that set. That's it. So the way we show that is we just write each interval and we put a union between them. So we're going to have B, which is 7 to infinity, union C, which is -5 to 5. By the way, do notice that finding the union of two sets or the intersection, they're both commutative operations. In other words, I could have just as well written -5, 5, union bracket 7 to infinity, and that would have been a correct answer too, because these are the same thing. In other words, in general, if you have two sets A and B, A union B is the same as B union A, okay? And A intersect B is the same as B intersect A. So both of them are commutative operations. All right, so B intersects C. So now we want to see what the aqua team and the red team have in common. Of course, as we just mentioned, they have nothing in common. So how do we indicate that? Well, two ways. If you want to use set notation with the braces, you can do so, just don't put anything in between. That indicates that the intersection is empty. Or better yet, you could use this more common notation, which is kind of a big O with a bar through it. It's called the null set or the empty set. So null set or the empty set. and these names correspond to both of those sets. Okay, so nothing in them. All right, A union C. So now we're going to combine the green team and the red team. So when we put those together, right, the green team and the red team, what do we get? Well, let's see. It looks like the green team already contains everything that the red team contains. So when you merge them, it's not going to contribute anything, the red team. So you just get what? You just get the green team. So in other words, the way to answer that is you can either say it's A, or you can actually write down what A is, which is the interval from -infinity to 10, like that. Okay. How about the intersection of the green team and the red team? See, of course, what do the red team and the green team have in common? All of the red team, right? So in this case, we're going to say C. So that's going to, or we can just write down what C is. That's the closed interval from -5 to 5. And that's that. That's how you would handle a scenario like that. Notice these two results are not accidental. Whenever one set is fully contained in another set, like C is fully contained in A, then their union is just going to be the larger of the two sets, right? Think about it. And whenever you take the intersection of two such sets where one is fully contained in the other, the intersection, of course, is going to be one of whatever the smaller set has in it. All right, and that's that. So make sure you can completely handle this on your own, and then we'll proceed. For our next problem, we're going to look at the intersection and union of these two finite intervals, and then we'll take care of these two finite intervals. So for this one, notice that the first thing we do, as we should always do, is to graph both intervals on the same real number line. And we notice that the interval from 3 to 7, which is closed, will look like this. So we have closed circle at 3 and closed circle at 7 with a line segment connecting them. And then the closed interval 2, 5 is depicted here in red. And for the first part, we're looking for the points of intersection. So that means what they have in common. And as you can see, that would be the region from right here to right here, right? So from 3 to 5. And we can write that answer as bracket 3, 5 bracket. So in other words, it will be closed because notice that 3 is in both sets. It's in the green set and the red set. So it's in the intersection, and the same goes for 5. It's in the red set. It's also in the green set. So that's the intersection of these two intervals. What would be the union of the same two intervals? In other words, the union of the red team and the green team. Notice that if we were to unite them without repeating, we would get everything from 2 all the way to 7, right? So we would have closed interval 2 to 7, like that. All right, and in this case, we have the open interval from -3 to 9 depicted here in red, and the open interval from 2 to 6 depicted here in green. And we want to know what's the intersection of these two sets. Notice that the smaller set, in the sense of length, the interval from 2 to 6, is fully contained in the interval from -3 to 9. In other words, everything that's in this interval is also in that interval. So what do they have in common? Obviously, the shorter set from 2 to 6. So the intersection of these two sets is just the same as the green team, so from 2 to 6. All right, so remember, it's going to be open on both ends because neither 2 nor 6 is in the intersection because it's not in the green team. In order for it to be in the intersection, it would have to be in both teams, right? How about the union? What happens when we merge the red team and the green team without repeating? Notice if we merge them, the green team isn't going to contribute anything to the red team. So we're just going to end up with the red team, and therefore we're just going to get the first interval from -3 to 9. All right, for this one, this is a visual one, and it's to get the point across the fact that this event that took place here with these two sets is not accidental. It always happens when one set is fully contained in another. So I want you to pause the video and see if you can answer these two problems based on this graph, and then restart the video. All right, so I'm hoping that you realize that because B is fully contained in A, the intersection of the two sets, what they actually have in common, is all of B. So the answer here is B. And because uniting the two sets would not contribute anything new from B, the union of the two sets will still just be all of A. And that's how you would approach something like that. So make sure you understand these before we proceed. For our next problem, we're going to find the intersection and the union of two open infinite intervals. Infinite, of course, in the sense of length. As we can see, here we have depicted the first interval in red, the interval from -infinity to 5, which basically includes all real numbers less than 5. And in green, we have depicted the second interval, which is from 3 to infinity, so all real numbers greater than 3. And notice that if we want the intersection of those two intervals, we're looking for points in common, and that would be exactly right in this region between 3 and 5. So we know that the answer here is going to be the open interval from 3 to 5. And it is open because neither of those two endpoints are going to be included, because neither of them is in both sets. And that's the only way either one would be included. All right, here we're going to unite these two sets, right? Union. So we're going to merge them, but not repeat. So if you notice, that's going to give you, putting those together, all real numbers. You may say, what about 3 and 5? 3 is not in this one. Yeah, but it is in that one. So when you merge them, it will be in the union. And the same here, 5 is not in the red set, but it is in the green set. So when you merge them, 5 will be in the union as well. So the union will be all real numbers. Again, we can depict that using R as well. All right, we finally have enough information to go ahead and solve compound inequalities. And if you have understood everything we've done so far, then this is going to be the easy part as far as technique is concerned. Now, compound inequalities come in two varieties. One is composed of the group of conjunctions, which are basically AND statements, and disjunctions, which are OR statements. Basically, in the case of our program, P and Q are just going to be two different inequalities. And we're going to solve them by solving each of those inequalities, and then if we're dealing with a conjunction, we're going to take the intersection of the two solution sets as the solution set for the conjunction, and in the case of disjunctions, we're going to take the union of the solution sets for the solution of the disjunction. So when you see conjunctions, think and then also think intersection and think in common. When you see or disjunctions, you want to think union and you want to think in either set. So we'll get into all that into more detail in a minute. A conjunction is a compound statement which is itself composed of at least two other statements connected with and. Conjunctions are sometimes intuitively referred to as and statements. Here are some examples of conjunctions. Today is Monday and today is the first day of the week. Another example would be x plus 1 equals 4 and y minus 3 equals 8. It's more mathematical. Another one is x is greater than or equal to 5 and x is less than 7. A conjunction is true only if both statements in it are true. The solution set of a conjunction is the intersection of the solution sets of the two statements in it. A disjunction, on the other hand, is a compound statement which is itself composed of at least two or more mathematical statements connected with an or. Disjunctions are sometimes intuitively referred to as or statements. Here are some examples of disjunctions. Today is Monday or today is the first day of the week. Notice all we did was change the and in the previous example to or here. And the same with these two next ones. They're exactly the same as the ones we encountered before. We've changed the and with ors. A disjunction is true if either statement in it is true. The solution of a disjunction is the union of the solution sets of the two statements in it. In the next few problems, we're going to solve two problems side by side. One will be a conjunction, the other will be a disjunction. And the interesting thing about them will be that we will be using the exact same inequalities in both of them, except that, of course, one will be an and statement or conjunction, the other will be an or statement or disjunction. And we'll see how significant the difference between and or is once we're done with these problems. So to do so, we'll go ahead and just start solving this first inequality. So we keep the x on the left side, we'll move the 3 to the right side, so it becomes -3. So we end up with x is less than 3. And then we solve this inequality, so we have x greater than or equal to -5 plus 4. So x is greater than or equal to -1. And of course, remember, we're going to have and at every step of this process. So now we'll go ahead and plot both of these graphs on the same number line, and we'll see if we can find the intersection of the two graphs so that we can find the solution set of the entire conjunction. So let me go ahead and set up the graphs and we'll proceed. In the meantime, you should go ahead and pause the video and see if you can graph it on your own before we go on. Okay, so here we have depicted this first inequality, x less than 3, in green. We notice that we have an open circle because it's not less than or equal to, it's a strict inequality, so 3 is not included. And for the second one, we've depicted in red, And notice that we do have a closed circle there because -1 is included in this set, because we want all the real numbers that are greater than or equal to -1. So because this is a conjunction, we're going to take the intersection of those two solution sets for our final solution set of the conjunction. So notice that what they have in common is exactly this area between -1 and 3. So we depict that down here for our final solution graph, and this is always recommended with these types of problems. Graph your solution set before you actually write it out. It's much easier. So do notice that we have a closed circle at -1 because -1 is in both of those sets, so therefore it's in the solution set, and open circle at 3 because 3 is not in the green set, so it's not in the intersection of the two sets. Now we can easily write the solution set. Solution set is going to be the interval from -1 to 3. It's a half open interval and it's closed at the -1 end because -1 is included. Now if we were to try to solve this, notice none of this would change, right? The only thing that would change is instead of an and at the end, we would have an or. So we don't need to go through all that. We just need to say we know we're going to get to this, x is less than 3, or x is greater than or equal to -1. Now we basically, the prep graph, so this first graph can be thought of as the prep graph before our final solution set. Notice that the prep graph will be exactly the same. The only difference now is going to be what needs to happen next, which is because this is an or, we need to take the union of these two sets. And of course, when we unite those two sets, what do we get? We get the entire real number line. So the solution set, when it's a disjunction, for the same two inequalities is very different. The solution set becomes all real numbers, like so. So be very careful about the difference between and or. As we said, it's very significant and you must pay attention to it. Here we have a very similar scenario. We have the same pair of inequalities separated by an and in the first case and or in the second case. So we have a conjunction on the left, disjunction on the right. So we go ahead and proceed to solve just as before. So we have 4x greater than or equal to 5 plus 8. So 4x greater than or equal to 13. And dividing both sides by 4, we get x greater than or equal to 13 over 4. For this one, remember with inequalities, we always want to keep the variable term on the left side. It'll be easier to interpret the solution at the end. So we have -10 minus 5, so we have -3x less than -15. Now we're going to divide both sides by -3, and we know what happens as soon as we do that, right? The moment you divide or multiply both sides of an inequality by a negative number, you have to change the direction of the inequality. So now we end up with x is greater than 5. All right, so we're now going to graph both of those inequalities on the same number line, and then remember that. Let me just repeat this here because I want to put the and between them. Of course, we have and at each step. All right, and we're going to graph them, and then we're going to see what the solution set is going to look like by finding the intersection of the two solution sets. Okay, so we have graphed the first inequality, x greater than or equal to 13 over 4 in red here. We do need to make sure that the position of these two numbers is correct. So we do realize this is just the same as 3 and 1/4. So therefore it should be to the left of 5. So the position is correct, the relative position. All right, and we have graphed the second inequality, x greater than 5 in green. And of course, this is a conjunction, so because it's an AND statement, the solution set for the conjunction will be the intersection of the solution sets of the two inequalities in it. So therefore, if we look at the intersection of these two sets, this is one of those cases where a smaller set is fully contained in a larger set. And if you remember, the intersection in such cases is always just the smaller set, right? So the solution set graph is right here. So remember, the first graph is just a prep graph, and the second graph is the one that will be the actual solution set graph. This is the prep graph, right? Now notice that we are now poised to write the solution set, which is just going to be this set right here, which is just parentheses 5 comma infinity parentheses. All right, so it's an open set from 5 onward, right? So basically all real numbers greater than 5, if you want to say it in words. All right, so as we know, all these procedures here are going to end up being the same, right? So at the end, we just need to make sure that we say x is greater than or equal to 13 over 4, or x is greater than 5. That's the only difference that's going to pop up here, right? Everything else will be the same, except in each step, instead of an and, we're going to have an or, and as well in the final step, right? So notice that this time, because it's an or statement, the solution set for the disjunction is going to be the union of the solution sets. So what happens when we take the red team and unite it with the green team? Remember, again, green team is not contributing anything. Red team already has everything that the green team has. So the union will just be the red team. So we have solution set equals bracket 13 over 4 comma infinity. Of course, we could write both of those solution sets in set builder notation as well. In that case, it will be all x such that you can say x, or you can say x belonging to R. Pretty much, since we're only dealing with real numbers at this time, we consider that to be obvious, so we usually leave it out. But if you really want to be technically precise, you can say x belonging to R such that x is greater than 5. So that's the set builder notation solution set for the first part. And this one, you can say all x such that x is greater than or equal to 13 over 4. And that is basically how we handle a problem like this. So make sure that you can handle this completely on your own without looking, and then we'll proceed. For our next problem, we're going to handle a similar situation again. The only difference between these examples are the solution scenarios that we want to make sure we can handle. So we'll go ahead and start solving this inequality first. So we have x is less than or equal to 1 is going to stay on the right side. We'll move the 4 over so it becomes -4, just as with equations, change sides, change signs. So we get x less than or equal to -3. For this one, we're going to go ahead and keep the negative x on the left side. We'll move the 7 over to the right, so it becomes -7. And now we get negative x is less than or equal to -2. So now we're going to go ahead and divide both sides or multiply both sides by -1. Dividing or multiplying by -1 get the same thing done. So it doesn't matter how you want to think about it, but that is what is going to happen. So now we know that the moment we do that, because we are dividing or multiplying by a negative number, we have to change the direction of the inequality. So instead of less than or equal to, we get greater than or equal to. Okay. So basically we end up with x is greater than or equal to 2. Of course, at each step we know there's an and involved, so just to write down the final outcome, we have x less than or equal to -3 and x is greater than or equal to 2. So now we're going to go ahead and graph both of these, and then basically, since it's a conjunction or and, we're going to find the intersection of the two solutions here, whose graph we will find in a minute, and then we'll have the solution for the conjunction. Go ahead and set up the graph on your own, and I will set up mine on this end, and then we'll compare our answers in a minute. So go ahead and pause the video and proceed with graphing both of those on the same number line. So here we have our prep graph where we show both inequalities on the same number line. We have x less than or equal to -3, so we put a closed circle at -3 and then an arrow to the left, less than, that means the numbers to the left of -3, and also x greater than or equal to 2, so again a closed circle here and then arrow to the right. Now remember, this is not the graph of the solution set. We've been doing it in 2 phases, so that this is our prep graph, right? So now we're going to use our prep graph to try to come up with the graph of the solution set. And remember, we're looking for the intersection of these two solution graphs, right? And as we can see, they have no intersection. It's empty. So the graph of the solution set here, what is it? It doesn't exist because the solution set is empty. Okay, so this happens sometimes, and this is one of those scenarios. We need to be ready for it. Now, you will see how different the scenario is when we deal with or instead of and. Of course, we know that the steps for solving the two inequalities are the same. So when we solve this, we're just going to end up at the end with x less than or equal to -3 or x greater than or equal to 2, right? So go ahead and do the preps graph as well as the solution set graph for these before you come to check that our answers agree. And that'll be great exercise. Okay, so now you should have come up with these two graphs. So the first one on the top is our prep graph, which we'll just put P next to it. And the second one is our solution set graph. Notice that this time, because we're going to handle a disjunction, we need to take the union of the green set and the red set. And notice that the union of those two sets is just going to be both of them joined together. So the solution graph is actually looks exactly like the prep graph, right? We just did it all in blue so that we can see this is one solution set. So now we can write the solution set very easily. And again, I always recommend with these kinds of scenarios to graph the situation first and then write the solution set. So the solution set here will be this piece, which is basically beginningless. And when we have a beginningless situation, we start at negative infinity. And then it does end at -3. Notice that it's a closed circle, -3 is included, so it's going to be bracket, union, bracket, 2, comma, infinity. So this is the solution set when the same two inequalities are involved in a disjunction or an OR statement, and when it's a conjunction, because we have to have x values that satisfy both of these conditions, meaning x values that are simultaneously less than or equal to -3 and greater than 2. And of course, there are no such x values. That's why this solution set is empty. But here we want numbers that are either less than or equal to -3 or greater than or equal to 2, which of course is all of them. All these numbers that are less than or equal to -3, as well as these numbers that are greater than or equal to 2. So a huge difference between OR and as always. The last thing left on our agenda for today is what we refer to as three-part inequalities. Inequalities of any of these 8 forms that we see here, basically x being between two values, right, are called three-part inequalities because of course they have 1, 2, 3 parts, right, in all of the cases, right? So they're all handled in a very similar manner, and we will demonstrate that actually they're nothing but conjunctions in disguise. We'll do the demonstration for this case, but it'll be exactly the same for all the others. So please pay attention to that and make sure you understand it. Note that when we write this statement right here, first of all, the way you would want to read this is x is between a and b. That's how you would want to read it in plain English. Notice that because there's no equal on either one, you simply would say between, right? You don't want to say inclusive or left inclusive or right inclusive or anything like that. You would only do that if one or both of these have or equal to signs as well. This is another way of saying, by the way, that a is less than x and x is less than b. So notice this is what we meant by saying these are conjunctions in disguise. These are actually and statements. It just happens to be that solving this inequality and this inequality will involve very similar steps. That's why we usually handle them together. So consider this example. It's a very simple example where we have x plus 3 is between 2 and 5. To solve this for x, we would want to subtract 3, right? The only thing with three-part inequalities being solved simultaneously is that you want to do whatever you do to one side to all 3 sides. So if we're subtracting 3 here, we're going to subtract 3 here on the left as well as the right piece as well. So now we end up with -1 less than x less than 2. And this will be what we will use to write our solution set. Now notice if you actually broke it up and wrote it as an actual conjunction, right? You would get 2 is less than x plus 3 and x plus 3 is less than 5. You would go ahead and subtract 3 from both sides, and you would do the same thing here. Here you would end up with -1 less than x and x is less than 2. And of course, if you lump those together, you just get this. So this is why, rather than breaking it up and doing it this way, we usually just handle these types of conjunctions simultaneously by just solving it as what we call a three-part inequality. Okay, so why don't you give this a try, see if you can manage it, and then come back to see if you did it correctly. All right, so our task is to go ahead and solve for x. So we're going to want to isolate this x term here. So first we'll go ahead and get rid of this -4, which of course would entail adding 4 to the middle part. And remember, whatever we do to one part of a 3-part inequality, we have to do to all 3 parts. So we need to go ahead and add 4 there and there as well. All right, so when we do that, we go ahead and combine these, and we end up with -9 less than or equal to 3x less than 8 plus 4 is 12. So now the only thing left to do is to go ahead and get rid of the 3, which we can do by dividing it off. So we're going to go ahead and divide the middle part by 3, which we can do without worrying about changing the direction or anything like that, because we're dividing by a positive number. Remember, we have to now do the same thing to all 3 parts. So we end up with -3 less than or equal to x less than 4, that is. So basically the solution set for this compound inequality, known as a 3-part inequality, is going to be all x values that are between -3 and 4. Okay, so we're going to now plot a graph of this situation. Go ahead and pause the video and do the graph, and come back and we'll compare our graphs. All right, so we definitely want to keep in mind that this scenario is left inclusive, so we're looking for all real numbers between -3 and 4, including -3, excluding 4. So you want to be really careful about such details. So we're going to have a closed circle at -3 and an open circle at 4, because 4 will not be included. Now, notice that we can now easily write down the solution set. Well, I'm going to leave this like this, because I'm going to write the solution set first in set builder notation. So that'll just be all x such that, all right. Notice sometimes we don't say belonging to R, because the fact that you're talking about inequalities itself indicates that you're dealing with real numbers, so of this type. So we can just say all x such that x is between -3 and 4 left inclusive. This is the set builder notation for the solution set of this 3-part inequality, which is really just a conjunction. And the interval notation will be bracket, remember, always starting point, comma, ending point. And if an end point is included, you put a bracket next to it. That's why there's a bracket next to -3, because -3 is included. And then 4, but this time parentheses at the end, because 4 is not included. That's how you solve these 3-part inequalities. Make sure you can handle it on your own, and then we'll proceed. All right, and here is our last example for today. And basically, we're going to be solving this 3-part inequality. And make sure that you treat it like any other, because I want you to try it on your own first. And the suggestion is to clear fractions before you proceed. All right, welcome back. I'm hoping you gave it a try on your own. Notice that the LCD of all the fractions in this particular 3-part inequality is 6, right? So we keep track of that. We put LCD is equal to 6. And now we're going to go ahead and multiply that LCD by all three parts of this three-part inequality. So we go 6 times 1/2 less than or equal to 6 times negative 6x plus 2 less than 6 times 2/3. So now we will go ahead and cross cancel what we can. Okay, so we notice that we can cancel the 2 and the 6 to leave us 3, cross cancel that is, and the 3 and the 6 here will leave us 2. So now we go through and carefully write down what is left after doing that. So we notice that we end up with 3 less than or equal to 6 times negative 6 is negative 36x, and then 6 times 2 is 12, so you get plus 12. Of course, that is 6 times negative 6x, not just negative 6. All right, and then less than 2 times 2, which is 4. All right, so now we have all nice integers, so much easier to work with. It's always the recommended method to clear fractions first. So now we're going to isolate this term by subtracting 12, and of course we need to do that to all three parts. Subtract 12, and we end up with negative 9 less than or equal to negative 36x less than negative 8. So now we're going to go ahead and divide all three parts by negative 36. So like this. When you're dividing or multiplying by a negative number, make sure you don't do it right there. Go to a new line and do it, because you know what needs to happen immediately, right? With inequalities, the very instant that you divide or multiply all sides by a negative number, you need to switch the directions. Notice both of those directions are going to switch. So now this, of course, is just 1/4, and positive 1/4 that is, and this one is now just going to be x greater than, this is going to become positive, and notice 4 goes into 8 2 times, and it goes into 36 9 times. Now, while you can leave it like that, it is highly recommended that you write it in its equivalent formats with less than signs. So in other words, we start at this end, we say 2/9 is less than x less than or equal to 1/4. You know that whenever you say a is less than b, that's exactly the same as saying b is greater than a, right? These are equivalent forms. So this time we went from this form to that form, okay? So the reason we do that is because now this will be easier to interpret as far as graphing is concerned. Go ahead and pause the video, take a moment to graph this and see what you come up with. All right, so of course we're going to have an open circle at 2/9, because 2/9 is not included because we want x greater than 2/9. So it doesn't say greater than or equal to. Notice I'm reading this from right to left when I say x greater than 2/9. Just like here, you say a is less than b if you want to read it from left to right. If you want to read the same expression from or inequality, I should say, from right to left, you would say b is greater than a. Remember, the larger number is where the opening is toward, the opening of the inequality symbol. All right, so open circle at 2/9, we want a closed circle at 1/4, and of course everything in between, right? So there's the graph of our solution set, and we can write the solution set now in the following manner. We can say S is equal to now, if we wanted in set builder notation, that's simple enough. That's all x such that this happens, right? Meaning 2/9 is less than x less than or equal to 1/4. And if we wanted in interval notation, we know we're going to start with parentheses because 2/9 is not included. And then, so 2/9 comma, and then 1/4, followed by a bracket because 1/4 is included in the solution set. Notice that you could check these very simply with at least one point by plugging in a value between those two numbers. If we go to the previous example, that's a particularly simple check, which I'll show you in a second. All right, my system had already erased that, so I'm going to show you how to check this one actually using a calculator very quickly. So what we're going to do is we're going to plug in an x value between 2/9 and 1/4 into this inequality and make sure that it becomes true, right? So let's say 2/9 and 1/4. Now that's a little bit hard to come up with what kind of value is going to be in between there. Well, it's a little bit difficult to come up with because they don't have the same denominator. But the easiest way to handle that, since calculators are available, is just get to the decimal equivalent. So when we take care of 2/9, for some reason my calculator is writing letters, so I need to get it out of that mode. Give me 1 minute. All right, so here we have it, 2/9. So we see we get 0.2 bar basically, and we'll take care of 1/4. That should be 0.25, right? So what we're going to do is we're going to pick a number between those two values, right? For example, 0.23 should be a good value, right? So we'll go ahead and plug in 0.23 in here for x. So we get -6 times 0.23, and then we're going to add 2. And what do you expect to happen as soon as I hit enter? It's not as dramatic as it is with equations, right? With inequalities, you have to see what they're claiming, right? We're claiming that if x value is picked in this solution region, then plugging it in should give you something between these two values, right? So let's go ahead and hit enter. And do we get that? Well, we have to see, we know what 1/2 is, right? Notice 1/2 is 0.5. And let's see, 2/3 is 0.66, etc., right? Now, is 0.62 somewhere between 0.5 and 0.666, etc., right? 0.6 bar. Notice it definitely is. So it looks like our solution set should be the correct one. All right, so that's a quick check. You can pick a sample point from the solution region, plug it in, and make sure it satisfies the original inequality, or in this case, compound inequality, which is also known as three-part inequality. All right, so that is how you would approach a problem like this, and hopefully that should help you handle these scenarios. All right, so this should pretty much do it for our discussion of compound inequalities. Make sure to watch it again if you need to, and always do it interactively, trying it while we're doing. In other words, we need to be doing this math together. It's not going to be a scenario where you're just going to watch, because if it is, there's not much learning going on. Okay, so that should do it. Stay safe, and we'll see you at the next video.